Hello and welcome to ToKCast episode 26. We're still on the multiverse and I tend to be talking more than I have in previous episodes. Thank you to the people who've been supporting the podcast, by the way. They're coming out more frequently precisely because of the additional support I've been receiving via PayPal and Patreon, so thank you for that. So we're going to be doing, at least after this one more episode. I was intending on this being the final episode for the multiverse, but just looking at the time that it's taken for each of these to complete, as in how long each episode's running for, I wouldn't like to make one episode go for 2 hours, and so for that reason, this one's going to probably be about an hour, and then the next one will be about an hour as well. And then that will be the last one on the multiverse before we move on to chapter 12. A physicist's history of philosophy. What we've been talking about so far in the readings from chapter 11 is the fictional story that David is telling in order to explain aspects of the multiverse theory which aren't often considered by people who explain the multiverse theory. One important aspect of that is fungibility. And today we're going to come more directly to this idea of entanglement as well. So we're going to have a go at explaining that. So to recap, what we had in a previous episode was that a device called a transporter had a voltage surge in it, in one universe but not the other. This is the quantum event. The quantum event happens in one universe but not the other. And quantum events are typically of this kind. We've looked at half-silvered mirrors, for example, where a photon could go through the mirror or bounce off. We've looked at interference experiments of different kinds, where, for example, Young's two-slit experiment, where if you fire a single particle at the two slits, it could go through one or the other of the two slits, perhaps neither. Perhaps it can take different paths through both as well. But there are options within the universe about where these particles could go. In the case of the story that David's telling, the voltage surge could have happened in the universe or might not have happened in the universe. And then the effects of that voltage surge, this quantum event, are amplified up to the point where the voltage surge, where it happens, jolts a particular person, and that causes them to spill coffee, and the coffee spill then leads to them talking to the person that's sitting next to them, and romance ensues. So we end up with this emergent kind of stream of information going on in one universe that didn't go on in the other. Okay, let's continue with the book. I've skipped a substantial bit, and I'm about to skip a substantial amount more. As I emphasized in the last chapter, this is the longest chapter in the book, and I am only partially doing it justice, so you really should read the entire chapter. My videos are just to provide additional context and exposition, I suppose. All right, let's continue. And David writes, "Now suppose that scientists on the starship know about the multiverse and understand the physics of the transporter, though note that we have not yet given them a way of discovering these things. Then they know that, when they run the transporter, an infinite number of fungible instances themselves, all sharing the same history, are doing so at the same time. They know that a voltage surge will occur in half the universes in that history, which means that it will split into two histories of equal measure. Hence they know that if they use a voltmeter, capable of detecting the surge, half of the instances of themselves are going to find that it has recorded one, and the other half are not." Pause there, just my reflection. Remember also in the last episode, we moved beyond this idea that there were only in fact two universes. That in fact there's an infinite number of universes, an uncountably infinite number of universes, all of which are fungible to begin with. They're all the same, and the same number of universes is maintained throughout any event which causes differentiation. So the idea of the multiverse is that we have a constant number of universes. It's just that they differentiate over time. They become different over time. And so prior to this voltage surge, there's a certain amount of universes, a certain measure of universes. You can't count them for reasons that are explained previously in the book on infinities. So instead what we have is this idea of a measure. So we have this measure of universes. Consider it analogous to measuring the length using a ruler. Okay, there's an infinite number of points between, the 1 centimeter point and the 10 centimeter point. Even though there's only 9 centimeters difference between them, there's an infinite number of points. And so instead of counting the points between 1 centimetre and 10 centimetres, we measure lengths to say that there's 9 centimetres between the 1 and the 10. Now we could divide that 9 centimetres in half to two 4.5 centimetre sections. So we're talking about lengths rather than counting points when it comes to measuring things. And so the same thing is true here of the multiverse. An analogous thing is going on where prior to the voltage surge happening, the measure of universes is such, and then after the voltage surge happens, the universe differentiates into two equal proportions. Now, it doesn't have to be equal in the true quantum theory. It can be any old proportion that you like. But assuming the simplest case here, we have half of the universes in which the voltage surge happens and half the universes in which the voltage surge does not happen. And all of the, I'm about to say things in those universes, but remember the universes are nothing more over and above the things that are in the universes. It's not like a universe is a receptacle for things, as David has said previously. And so the people in those universes, there's uncountably infinite numbers of fungible instances of those people, as there are for you. And as I've said before, well, that seems preposterous. What on earth would it feel like to be many different people? Exactly as it does now. Now, if you're struggling with that concept, well, depending upon who you are, perhaps you struggled when you first perhaps figured out that you didn't have an immortal soul. And some people who believe in the immortal soul, who are religious, if they undergo a transformation in their mind where they realize that they don't have an immortal soul. Now, if you're not a religious person, you might very well be asked by a religious person, it's preposterous to think I don't have an immortal soul. I can feel that I have an immortal soul. They're feeling their mind or they're feeling their consciousness, something like that. So I think it's no more of a great jolt going from believing you have an immortal soul and you have a certain sense of having an immortal soul to no longer believing that you have an immortal soul. This is the kind of transition that I would think it's analogous to. Going from thinking you're just a single instance of a person in a single universe to you are uncountably infinite numbers of instances of people in the multiverse. You're a multiversal object. I don't think this is a huge transition. Okay, so I'll just step back a bit. I'll reread some and then I'll move forward again. So David wrote, hence they know that if they use a voltmeter capable of detecting the surge, half of the instances of themselves are going to find that it has recorded one and the other half are not. But they also know that it is meaningless to ask, not merely impossible to know, which event they will experience. Consequently, they can make two closely related predictions. One is that, despite the perfect determinism of everything that is happening, nothing can reliably predict for them whether the voltmeter will detect a surge. The other prediction is simply that the voltmeter will record a surge with probability 1/2. Thus, the outcomes of such experiments are subjectively random from the perspective of any observer, even though everything that is happening is completely determined objectively. This is also the origin of quantum mechanical randomness and probability in real physics. It is due to the measure that the theory provides for the multiverse, which is in turn due to what kinds of physical processes the theory allows and forbids. Notice that when a random outcome, in this sense, is about to happen, it is a situation of diversity within fungibility. The diversity is in the variable what outcome they are going to see. The logic of the situation is the same as in cases like that of the bank account I discussed above, except that this time the fungible entities are people. They are fungible, yet half of them are going to see the surge and the other half are not. Pause there, my reflection. So it sounds preposterous that you are made up of all these fungible entities, that there are these many different universes. But the fact that it's surprising or astounding is not a reason for rejecting it, nor a reason for getting unduly emotional, except to be curious and interested and fascinated perhaps, positive emotions. It's just what the science is telling us. But it's remarkable to me that some people have visceral negative reactions. And so I'm going to have a little diversion here. And we're going to listen to a different podcast. We're just going to listen to a few minutes of the excellent Brett Weinstein's Dark Horse podcast. And this is an episode in which Brett Weinstein talks to Sam Harris. These two people are great intellects. I love listening to Brett Weinstein. I think he's a fantastic thinker, great biologist, a person who is able to sensibly reflect upon culture at this moment. And of course, Sam. Sam is a great rational thinker, typically measured in the way he talks about things. He doesn't get overly emotional. And here, in what we're about to listen to, they're discussing the multiverse. Now, as much as I admire these two great public intellectuals, I think here they make terrible missteps in simply appreciating the physics. And I think it's not only because they're stepping outside their domain of expertise. I don't have a problem with people doing that. After all, this is what I do quite often. The concern I have is they're not applying the same standards, intellectual standards, to this theory as they would to any other theory that a scientist might have. And in particular, when it comes to evolution by natural selection, all of the objections that I'm sure that Brett hears from creationists or other people who reject Darwinism or neo-Darwinism, all of those objections are precisely the kind of objections. They're on a continuum with the objections that he's about to raise about the multiverse. Okay, so rather than go into a longer preamble than that, let's just get into listening to the podcast. By the way, this is episode 8 of Brett Weinstein's Dark Horse podcast. It can be found on YouTube. It can be found on iTunes. His podcasts are typically very long conversations, which are excellent, of the length of 2.5 hours or so. We're only going to listen to a few minutes, just the part that's about the multiverse. And it comes up in a discussion, just by the way, about free will. And in terms of free will, Sam and Brett seem to be in furious agreement about the non-existence of free will. So let's hear what they have to say.
Right. Yeah, well, so this could be a semantic difference between us, but let's talk about what you think that scintilla of freedom actually is.
Okay. So first of all, it is utterly dependent on us not living in a deterministic universe. If we live in a deterministic universe, then I don't understand a damn thing, and it's game over for Brett. Assuming we don't, and I think the physics is pretty clear, there's no reason to think we do. There's quantum uncertainty, and the fact that there is quantum uncertainty means that uncertainty can exist at higher levels through various mechanisms.
Well, or we live in a universe where, if you take the many worlds picture seriously, which, again, is hard to do, but many physicists do at this point.
Sam has just said there that it's hard to do. It's hard to believe in this idea of the multiverse. Very well. Many things are hard to believe, I suppose. Almost anything in science is hard to believe. Anything of interest is hard to believe. The universe is 13.7 billion years old. The universe is as large as it is. The universe contains as many stars that it does. We have preposterous numbers to some extent when talking about these things. The number of possible organisms that could be produced using the DNA code, preposterous, perhaps infinite in size. Now, just putting aside the fact that I don't think that the multiverse adds too much to this concept of free will. I think that, the concept of free will that I have anyway, this idea that it's an emergent feature of human minds coupled to their creativity, causing them to be able to do things that are inherently unpredictable. I don't think that that's really helped by the multiverse, but it's certainly not made any more difficult. I don't think the multiverse really has a lot to do with free will, to be honest. But putting that aside, what is the scientific criticism of the multiverse that Sam and Brett are sort of about to get into here? That's what we need to listen out for. Or what is the philosophical criticism, the philosophy of science, or the epistemological criticism? Because Sam so far has said it's simply hard to believe. But the feeling that something is hard or difficult, hard to take seriously, is not a reason for rejection. It could be a reason to look into things a little bit more deeply. And of course, I'm not going to get into right now the fact that Brett clearly thinks that determinism and free will cannot go together. Okay, I'm not the only one who thinks that they can. Daniel Dennett's another person. Reasonable people can have differences upon this. Okay, and often it comes down to these silly definitional games. And if we define free will in the way that people who say they're not compatible is to be defined, well, then I agree that sort of free will cannot possibly obtain. If free will has to mean something like beyond the laws of physics, a supernatural force that allows you to make choices outside of what physics permits, or an uncaused cause, okay, if it's something like that, if that's what free will is, then I agree that doesn't exist. Free will cannot be supernatural and it cannot be an uncaused cause. So I'd like to preserve the concept of free will, the kind of free will that people typically who believe in it, I think they have, or at least to come to understand it a little better. And so that's the reason I think that free will and determinism have to go together. And if you don't want to call what I think free will is free will, if you want to call it something else, I'm okay with that as well. Okay, but I typically think that when people are talking about choices and free choices, it's a very simple concept to just use the term free will. I've got numerous blog posts on my website about free will. Anyway, we're not here to talk about free will. Let's go back to Brett's podcast.
We live in a world where everything that can happen does in fact happen somewhere, right? And you don't know which one of these worlds you're in, right? So it's a new kind of determinism in a way, which is like, every gradation of possible difference in this probability space, which is this conversation between us, is spawning yet another universe in which precisely that thing is happening, as deterministically as one billiard ball hitting another. But the uncertainty is we don't know which one. We don't know whether we're in the universe where we both start speaking Mandarin right now for reasons we can't understand, or we're in the universe. I'm pretty sure we're in the universe where we're going to stick with English, but whatever surprises are here can still be understood deterministically in that picture.
Okay, so I think that's great. I think that's more or less correct. Perhaps one of the misconceptions that people have when they reject this is that although what Sam has said there is quite true, we don't know if we're in a universe where we're going to start speaking Mandarin all of a sudden, even though neither of them can speak Mandarin. That's a physically possible universe. Some people think that it's somehow likely or common or I don't know what. They think the mere possibility that is a possibility is a refutation of the theory. But it's not. There are possible organisms that one could create using DNA that would be absolutely astonishing, but terribly unlikely. No doubt there is a physically possible organism that can evolve, which is highly unlikely to ever evolve in the history of our universe. Interestingly enough, however bizarre the organism is, if it's physically possible, it will evolve somewhere in the multiverse. So these are kind of related issues, to be honest. But, we could imagine a scenario, an alternative history where we never had any fossils. We never had any evidence of dinosaurs. Imagine that possibility. It's possible. I mean, fossils are hard to come by. They only result under very, very rare circumstances. The dinosaur has to fall into a lake of mud of just the right kind and get covered up immediately in an anaerobic environment where the oxygen can't get to it and the bacteria can't get to it so that the bones are preserved, blah, blah, blah. There's a lot of coincidences that have to happen to preserve dinosaurs. I can imagine a world where dinosaur fossils were far, far, far more rare than what they are. And it could have been the case that by 2020 we had never found any dinosaurs at all. But we may have found evidence for evolution and evidence that DNA is the thing that contains the genes, which is the unit of evolution. Now imagine if we had a very similar universe, the universe is basically the same as ours, but it's a universe in which fossils had never been found. If somebody like me had come along doing exactly a podcast like this and then said, well, DNA allows things like, DNA would allow things almost like dragons. I'm not saying these dragons can break the laws of physics. I don't think they'll probably be able to breathe fire. But I could imagine a flying dragon. Or I could imagine a dragon that is, 50 meters long, lumbering around on land. I could imagine that biologists might very well say, well, that's not possible. The limbs are too big, it's too heavy, it wouldn't be able to get enough oxygen into its lungs, there's no way these things could fly. But of course we know, even though people in that universe don't, that dinosaurs are eminently possible. There were pterodactyls, big flying things that may as well have been dragons without the breathing of the fire. There were Brontosaurus and Diplodocus. There's really big, huge dinosaurs that ate trees. They were physically possible. They actually existed. But I can imagine a biologist being so incredulous, and many people being so incredulous, if we didn't have fossil evidence, as to reject outright even the possibility, given DNA, that such a thing could evolve. But they can. And in our universe, we happen to know that they can. Now, I don't know what the repertoire of all different organisms is. It's infinite, but it will be an interesting, project to try and figure out, could you evolve an animal with wheels? I don't know. Could a mammal evolve such that it can exist in very sub-zero temperatures or above 100 degrees Celsius? I don't know. Okay, but these are things which are possible or not given the DNA. And so there are things that are possible or not given the laws of physics. But I think Sam has echoed kind of what I've said in the last episode and the episode before that and the episode before that, which is something that David emphasizes quite often, is that the quantum multiverse is simply determinism. It's a deterministic theory. And it, unlike certain other so-called interpretations, which are not deterministic, they attempt to introduce randomness into the world. Okay, let's keep going. We've got the next key bit by Brett.
Well, I've never regretted not speaking Mandarin more than I do right now. But so here's the thing: I resent the many worlds interpretation.
So there we have it. There it is. He resents the many worlds interpretation. It's an emotional reaction. Where else in science is this a legitimate form of criticism? Especially from an outsider. Brett would be right if at one of his public lectures on evolutionary biology to reject outright a conservative religious person who stood up and said that he resented the theory of evolution by natural selection. He would be right to reject it as a legitimate criticism. It's not. It's not a scientific criticism. It's a sign that the person is having a visceral emotional reaction because they don't understand it. That's all. It's no sin not to understand something, but it's possibly a misstep to then get exceedingly emotional about it, to the point where you're using a word like resent. Now, perhaps I'm reading too much into resent until we hear the rest of what he has to say.
I'm actually not convinced that it's exactly wrong, but I am convinced that at best it is a very stupidly explained way of phrasing something that nobody can seem to phrase so that it is not insane.
Okay, so we can take the point that explanations are hard to come by and difficult to express. What did Karl Popper say? It is impossible to speak in such a way as to not be misunderstood. So any explanation of a fundamental phenomena is going to be difficult at times for people to grok, to understand. But insane and stupidly explained. Perhaps the explanations that Brett has heard have been stupidly explained or insane to him. It's not the sort of language I think I've ever used about a scientific explanation. There might be two kinds of people in the world when encountering a deep, subtle explanation for the first time. In fact, they're summed up by my mother and my father. My father will often be somewhat like Brett Weinstein. He will say, that's stupid, and he will reject it outright because it seems too outlandish. My mother, on the other hand, will just say, I don't understand it. I don't get it. That's it. So when it comes to the multiverse explanation, I think it's astonishing. And when I first heard it, I thought, that's astonishing, that's astounding, that's surprising. But as for stupid and insane, they're not normally words that I tend to apply to scientific theories. Brett himself would have been in the position that some physicists are in with respect to explaining aspects of quantum theory. Brett, as a professional biologist, has probably delivered public lectures where there's been conservative religious people who've come up to him after the lecture or perhaps during the questions and been unable to fully appreciate what Brett has been saying about evolution by natural selection. Brett must know what it's like to deal with a person who has an emotional, a visceral reaction to something new that's simply science. It is not a valid criticism for a creationist to say evolution by natural selection is insane. I mean, they can use those words if they like. Free speech is permitted, but it's not a valid scientific criticism. It's not a valid philosophical criticism. All it is throwing shade. It's insults. It's not actually seriously engaging with the theory. Evolution by natural selection is an explanation of how the diversity of species has arisen. It's an explanation of the similarity of DNA and the similarity of physiological structures. It's an explanation of the fossil record. And as astonishing as it might be to many people who hear it for the first time, or especially religious people who believe that it runs counter to their deeply held religious views, it merely running counter to deeply held religious views or deeply held perpetual errors that a person happens to carry through their life is again no criticism. Brett would be right to dismiss a religious person who was criticising, okay, in scare quotes, because it's not a valid, genuine criticism, but having a go at evolution by natural selection on the grounds that it's stupid or on the grounds that it is insane. So just because the explanation that some people have heard for neo-Darwinism thus far seems preposterous, that's no reason for thinking the theory or those who endorse the theory are either stupid or insane. In fact, it says far more about the person levelling those allegations against portions of the scientific community, because it's not a genuine scientific criticism. It's more a reflection, in the case of the religious person, some kind of supernatural bias, the magical thinking. And again, as I've said before, I find it far more astonishing to think that all of the entities described by the equations of quantum theory, including the Schrödinger wave equation, all those many, many entities do not actually exist as the theory says that they do, but rather the act of observation causes them all to vanish from science and from reality, leaving only one that we do observe. That's a strange impulse to have, a psychological impulse, that somehow science is about you and your personal psychology and capacity to observe things, rather like thinking that the only planets that exist in the universe are the ones so far observed. That would be absurd. The theory of planetary formation extends beyond what we can observe into regions of the galaxy and the universe that we have no hope of observing right now. But we know planets are there. Know in the fallible sense. Not know in the traditional, I'm justified in believing that such a theory is absolutely true, namely the existence of planets beyond those that we can see so far, but rather an understanding that the theory of planetary formation is deeper than what our bare observations are revealing to us. So too in fundamental quantum theory. We may only observe photons striking the screen at one place at a time. But the fact that they do strike the screen at this place rather than that place means that they've been influenced by something unobserved, namely photons in other universes. And we've been through that. Anyway, let's keep going with Brett and Sam.
And
Well,
so,
it is the I think on its face, the hardest thing to believe that still is seemingly believed, or at least paid lip service by it might even be a majority now of physicists. I mean, it was the last poll I heard, it was something like 35%, but it's getting there, and it is the strangest picture of reality that you could imagine.
Okay, the strangest picture of reality that you could imagine. Well, I just simply disagree. It's not. It's not the strangest picture of reality that you could imagine. That's simply a failure of imagination on Sam's part. But I don't think he actually really believes that, because there are many things that are far stranger to imagine that people have taken seriously over the years. Great minds. David Lewis wrote on the plurality of worlds, a philosophical defense of many worlds. But it wasn't many physically possible worlds, it was all the logically possible worlds. And so he endorsed a kind of realism about this. And by the way, David Wallace, David Deutsch, David Lewis, I don't know if you have to be a David to really make breakthroughs in many worlds, but it seems like it helps anyway. So David Lewis, his book on the plurality of worlds, talks about how all logically possible worlds obtain some way in reality. That has to be an far infinitely stranger, and therefore more difficult to imagine, picture of reality on Sam Harris's account than anything that David Wallace, David Deutsch, or Hugh Everett have ever come up with. Because the many worlds interpretation of physical reality represents but a tiny, tiny sliver of all the possible, logically possible realities that are out there, all the logically possible worlds. Because those other logically possible worlds will obey different laws of physics. The physically possible worlds of the multiverse all obey exactly the same laws of physics. And so the class of all different possible, logically possible worlds, that is a far, far greater number, and therefore a stranger picture of reality. But again, I just think it's kind of a failure of imagination to think that there's nothing stranger than this. I insist again that all physicists endorse something like the Schrödinger wave equation as a serious representation of reality to some extent. Those who do not endorse the many worlds interpretation say that the Schrödinger wave equation in some way represents reality prior to the act of observation, and then the act of observation, consciousness, whatever you want to call it, the observer effect, is the thing that causes the collapse of the wave function. So all the realities disappear, but one that we observe. That, to me, is more difficult to imagine. And it's this additional assumption that what the equation is telling us about reality is true until the act of observation, when it's the act of observation that is bringing into reality what is true. That's an additional assumption over and above what the many worlds interpretation is telling us. The multiverse just says that reality is what quantum theory, what the equations of quantum theory describe. That's it. We're not adding anything to it. But collapse models do. They add something. They add this additional assumption that observation is causing reality to be the way that it is. That's bizarre. That's really bizarre. And as for hard to believe, that's far harder to believe. This idea that observation is the thing that is causing little particles to do one thing rather than another. It's your act of observation that causes all the realities to disappear but one, and therefore all of the electrons and photons that happen to be in your experiment to follow one path rather than another. There's spooky action at a distance if ever there was some. This strange woo-woo force coming out of your brain and affecting subatomic particles at a distance from you. That seriously is what collapse models are insinuating about reality. That makes no sense. That's a weird metaphysical jump. I don't get it. But I wouldn't say that people who endorse that are necessarily insane or stupid, or that's necessarily an insane or stupid theory. That's not a scientific criticism. But the criticism that you must add additional assumptions, like the power of observation causes the vast majority of reality described by the equations of physics to disappear, that is a fair criticism, that we shouldn't have such an assumption, that no assumption is needed. Because to introduce such an assumption is merely to try to get the theory to comport with your biases, with the biases that we're hearing expressed here, that it's just too hard to imagine, that it's difficult to believe. Well, it doesn't matter if it's difficult to believe. Evolution by natural selection is difficult for some people to believe. But the difficulty in believing it has no bearing whatsoever on the actual correctness or otherwise of the theory or of the explanation as being the best explanation that we have. Let's keep going.
I think you're being too nice.
Yeah.
It's stupid. The idea that universes are spawned to deal with the difference between the thing I dropped hitting one carpet fiber and the next.
It's hilarious to me. I mean, Brett's having an emotional reaction. Brett Weinstein's having an emotional reaction. A very negative, visceral emotional reaction here, saying it's stupid, it's insane. I will get emotional about science at times like this when people are having ridiculous reactions. I mean, there's no reason to say that it's stupid, because it's not. It's not. If you understand it. And I think it's reasonably clear that he doesn't understand it, or that he's been presented with a strange version, that he hasn't read the books of David Deutsch, let's just say. And I would recommend to you, Brett, please pick up The Fabric of Reality, in particular the chapter called Shadows. And if you're not convinced after that, very well. But I wouldn't say that people who write such books are stupid or insane. And this is not reasonable philosophical discussion. It sounds measured and reasonable, and Brett, under normal circumstances, is a great mind, a great intellect. I love listening to him. He's fantastic, as I say, in terms of biology, really original thinker in certain respects, I think. In terms of analysing culture right now, both Brett and Sam, brilliant at that. Not everyone who steps outside of their domain necessarily makes such strange, sweeping generalizations. I will comment frequently about aspects of economics or history that I don't necessarily have expertise in, but I don't usually regard, even though with whom I have a serious disagreement, as stupid or insane, nor their theories necessarily. Okay, let's keep going.
Sorry, that's not how nature works.
It's a different view of parsimony than I have intuitively.
It's a total rejection of parsimony. It is the opposite of parsimony.
Okay, so there we go. He, I guess, misunderstands parsimony. And I think Sam is about to correct him on that, by the way, and Sam does a very, very good job of correcting him on it as well, I think. But parsimony is just this idea that you shouldn't increase the number of assumptions beyond what is absolutely necessary in order to get your explanation across. Now, this is, in my mind, it's the same as Occam's razor. Now, I've had university lecturers at some point try and tell me the difference between what parsimony is and Occam's razor, and I've never got it. I've never understood it. Apparently, they're subtly different things, parsimony versus Occam's razor, but I use them interchangeably. And I'm going to continue to use them interchangeably here for the moment, unless someone can provide me with direction on where I've gone wrong. And so given that they're both about assumptions, let's just go to The Fabric of Reality, where David writes about this precise objection, that the many worlds is somehow a rejection of parsimony or rejection of Occam's razor. This, in fact, was the criticism that Professor Paul Davies, had of the many worlds interpretation, that it caused the number of universes to multiply beyond all reason in order to explain the one universe we do observe. But as Sam, I think, says in the next bit, that's a concern about the bricks and mortar of the theory rather than the assumptions in the theory. Now, I've already mentioned, the idea of exoplanets, planets that are beyond the solar system. Now, we only found the first one, I think, back in 1994, something like that. But our theory of planetary formation prior to 1994 predicted that there should be planets going around other stars. Now, it would be a violation of Occam's razor not a correct use of it, a violation of Occam's razor to say those planets do not exist. That although the theory of planetary formation says gas giants and little rocky terrestrial planets should be orbiting perhaps a majority of stars, it would be wrong to say, however, to take that theory seriously would cause the number of planets throughout the galaxy and the universe to proliferate beyond all reason. No, well within reason. And in fact, today we can see planets out to some, I think, 1,000 light years going around stars here in the Milky Way galaxy. But it's not very far. Okay, the other side of the galaxy is 120,000 light years away. And the next nearest galaxy is 2.2 million light years away. And we can see galaxies off to, many billions of light years away. We have no hope at the moment with present technology of seeing planets going around stars in other galaxies. But we know there must be planets going around stars in other galaxies because our best theory of planetary formation says that when a star forms, it will form from a cloud of gas and dust, which will then have a disk of material rotating around that star, some of which will clump together to form planets. Now, that's a very simple idea, with very small number of assumptions leading to this proliferation of matter, the bricks and mortar, as Sam will come to say. And so proliferating the bricks and mortar is not a violation of parsimony. It's an endorsement of it. It's a correct use of it. So let's go to the fabric of reality. Okay, so David, this is in the chapter called A Conversation About Justification, page 160 of my paperback here. And David is talking to a crypto-inductivist. The entire chapter is a refutation of the inductivist picture of knowledge. And he's arguing with a person about what the correct theory of gravity is. So it's in the context of what we should think our correct theory of gravity is, and on the basis of what should we think our correct theory of gravity is the correct theory of gravity. So we're not going to go into that, but the entire argument that David is about to use here, that I'm about to read, applies in this situation. So again, just to reinforce in people's minds, we have certain equations of quantum theory, one of which is called the Schrödinger wave equation. And the Schrödinger wave equation explains, the Schrödinger wave equation can be used to describe all of the positions, for example, that an electron has around the nucleus of an atom, let's say. And so this gives us the wave function, and it predicts that the electron will occupy multiple positions simultaneously around the nucleus of an atom. So the electron is not in one spot. It is physically not in one spot according to the equation. Now, if we take that equation seriously, then we say, okay, so the electron is not simply in one spot. It's in multiple different places at the same time around the electron. But when we go to observe it, we only ever observe the electron at one place. And so this is why some physicists, some people who look into the theory say, well, it's the act of observation that causes the collapse, so it's said, of the wave function to one point. And we see all the possibilities disappear except for the one that we do observe. Now, that's an additional assumption. The act of observation renders the equation invalid. Prior to the act of observation, the equation is a description of reality, but the act of observation causes the equation to cease to be universally valid. It's not valid at the point of observation, sometimes called the observation problem. But if we have equations of orbital dynamics, let's say, and thermodynamics that explain how stars and planets form from gas clouds, and those equations describe how most of the mass ends up at the center as a star, and the rest of the mass ends up forming planets, it would be ridiculous to say, again, that those equations cease to be valid except in cases where we can point a telescope at a star and see the planets orbiting the star. No, your act of observation isn't the thing that brings reality into being. The act of observation is just another part in the chain of science. It doesn't affect all of reality. But the collapse models, which includes the Copenhagen interpretation, and basically everything except the many worlds interpretation, the multiverse, all of those say there is this weird spooky action at distance where the act of observation causes all the realities to disappear but one. Okay, so that's the additional assumption. The additional assumption is observation causes all the realities but one to disappear. Okay, so now I'm going to use the fabric of reality in David's words to criticize that. And David writes, So your additional postulate is not just superfluous, it is positively bad. In general, perverse but unrefuted theories which one can propose off the cuff fall roughly into two categories. There are theories that postulate unobservable entities, such as particles that do not interact with any other matter. They can be rejected for solving nothing. Occam's razor, if you like. And there are theories like yours that predict unexplained, observable anomalies. They can be rejected for solving nothing and spoiling existing solutions. It is not, I hasten to add, that they conflict with existing observations. It is that they remove the explanatory power from those existing theories by asserting that the predictions of those theories have exceptions, but not explaining how. Okay, and I won't read the rest there. But that's perfect. Okay, end quote, by the way. That's exactly what anyone who rejects the many worlds interpretation, the multiverse, as a literal description of how reality is, as best we know, in favour of any other interpretation that adds this additional assumption that, again, that causes them to remove the explanatory power from the existing theory. So the existing theory being that all these possible realities do exist, that's what the equations say, and to add this additional assumption doesn't make things simpler, it ruins the explanatory power of that existing theory. Okay, so let's keep going.
Well, I put this to, I think it was Max Tegmark in a podcast I did with him. I think it was Max. And it was just a different view of parsimony. It was not, it was kind of privileging the mathematical parsimony over the bricks and mortar parsimony. I think that the many worlds was
very
not
well said,
was not the result of adding lots of assumptions or epicycles or something that was jiggering a theory. It was just a brave acceptance of the consequences of what this, we should say that, and again, I'm not a physicist, we should drag your brother in here to get into more of these details, but there's no picture of quantum reality that tracks our common sense intuitions about how the world should be. So you're left accepting something, at least at this point, that seems frankly bizarre, but many worlds seems about as bizarre as anything I could imagine.
Again, a failure of imagination there by Sam. But I think everything else he says there is absolutely fantastic. That's fantastic. You're left believing something strange, no matter what you pick. Okay, it does seem strange on first reading. In the same way that those lights in the sky, those little pinpricks of cold white light that we see when we go out into a bright night sky, are literally suns like our own, with planets going around them. That's astonishing. That's hard to believe when you first hear it as a child, if you can remember your mind being expanded by that. But as a child, people are very accepting. They don't have all of these irrational hang-ups about things. Some older educated people do, okay, myself included. But we're hearing now of some, what I would say are hang-ups from people. Now, Sam also says there, it's just of the multiverse theory. It's just a brave acceptance of the theory. Now, that's telling, I think. That is telling. Why brave? Why would one need to be brave in order to expound this theory? Would it have anything whatever to do with being thought stupid or irrational, or someone who endorses a stupid and irrational theory? That when you end up hearing those kind of, again, scare quotes, criticisms, those kind of insults or dismissive gestures, really, no wonder so many physicists don't endorse it or profess not to endorse it, because it's a reasonable, I think, fear to be thought stupid and insane simply for explaining what the science says. Now, biologists used to have to go through this. Not as much anymore. But we all know about the Scopes monkey trial, don't we? We know that biologists historically have been attacked as insane, stupid, heretics of some sort. And so, rightly probably, many didn't exactly get on the pulpit and try to explain evolution by natural selection. Now, back then, we had religious people shutting down the scientific debate. Now, I'm not saying that Brett's precisely shutting down the scientific debate, but it's in that tradition of dismissing as irrational people who are suggesting something, well, not exactly new here. I mean, we're talking about a theory that was first proposed in, 1950-something. So it's been a while. It's been a long time. And as David Deutsch has regretted, it's such a shame that physics in this area hasn't moved past concerns about taking the theory seriously for fear of being thought stupid or insane. And hence Sam's quite right, that those who have taken up the charge by taking this theory seriously are brave. And they should be lauded for having done so, in the face of people who are not willing to engage seriously in the debate, but instead throwing shade, one might say, which is unfortunate. It's unfortunate. And again, I think Brett's better than this in the way he's come off here. Maybe I'm being a bit harsh, but really, stupid and insane. Let's keep going.
No, you're not left with accepting it. And again, I'm not rejecting it in a formal sense. It may be an insane phrasing of something that could be phrased rationally from some other perspective. But as phrased, it really is the rejection of the idea of parsimony, and not for a good reason, just because, I mean, actually Eric does have a term for this sort of thing. I hope he won't resent my applying it here. I think he would, but desperation physics.
Imagine, saying of the neo-Darwinism, theory of evolution by natural selection, that the unit of selection being the gene that is on DNA, and that code being universal for life forms. Imagine simply rejecting that on the basis of being desperation biology, that it's stupid and insane. Because it is remarkable to think that whatever the organism is, it has the same code, the same DNA code. And if you were to look at two DNA strands side by side, one that was for bacteria and one that was for a human being, the average person would barely be able to tell any difference. In fact, I'm pretty sure you wouldn't be able to tell the difference without properly analysing it in the laboratory somewhere. That if you simply magnified up the DNA strand and looked at the two double helices, you wouldn't notice much difference. So that's a remarkable idea, that the information, genetic information, can code for such two vastly different structures, a microscopic organism on the one hand and a fully functioning human being on the other. Many things are astonishing. It'd be interesting to ask Brett Weinstein. We know that, for example, fossils are extremely hard to come by. They are a great series of coincidences usually has to occur in order for a dinosaur to have been fossilized, so far as we know. A dinosaur has to die in a shallow pool of mud and be covered over rather quickly with more mud in an anaerobic environment without oxygen, so the bacteria doesn't eat it away too quickly, so that the bones can be ossified, turn to rock over time. So this series of coincidences has not happened frequently. We don't have that many fossils. We could be living in a world where conditions were such that we had almost no fossils at all, perhaps none. Let's say we lived in a world where there were no fossils, for whatever reason. The bacteria tended to eat things more quickly than what they do, so there was no chance for the bones to be ossified. Or we lived in a world where, on planet Earth, the mud just wasn't deep enough, so all of the dinosaurs that ever died rotted away very quickly and nothing ever got preserved. Okay, I can imagine a world like that. I'm sure Brett and Sam can imagine a world like that. Imagine today, therefore, in such a world, if a biologist came along and said, do you know what, I think that in the past, although there is no record of it, I think in the past, according to what I know about DNA and genetics, there might have been, hundreds of million years ago, walking the earth, dragon-like creatures that flew through the air. Perhaps they didn't breathe fire from their mouths, but they were huge lumbering lizards, 50 meters long or more, weighing hundreds of tons. Now, that's a possibility. In fact, we know that in our world, that's a reality. To reject that as desperation biology would be wrong. It's a testable theory that if you came up with such a theory, you might, if you search long enough, even in such a world, find some kind of evidence of that. Perhaps you will find an egg preserved in amber somewhere. Perhaps you will find, as they did in Jurassic Park, the blood inside a mosquito preserved in tree sap somewhere. And then you'd be able to figure out, once you've done analysis of the DNA that's in there, you'd find dinosaurs. Okay, but as it is, in our world, we do have fossils. And so we don't have to debate the reality of dinosaurs or not. But we could be living in a world where we would be. Okay, let's keep going.
But it's not even, just forget about many worlds for a second. Just imagine a universe that is infinitely large. Right? Now, one of the probabilistic consequences of that scenario is that if you just go far enough in any direction, again, you run into the same problem. Anything that can happen will happen an infinite number of times. Right?
Yep.
I mean, that's how big infinity is. So there are an infinite number of identical copies of us having infinitely similar and slightly different conversations than this, an infinite number of times, simply if you make the universe big enough. I mean, that just falls out of probability theory.
Right.
I don't think the way that Sam's explained that there is correct. After all, one could have an infinite universe, infinite in size, that is utterly featureless. We may live in a kind of universe like that. That beyond the horizon of what we can see, in the accelerating universe, that the universe just keeps getting larger and larger and larger, infinite though it is, and more sparse. In the distant future, if the universe does in fact last forever, under this accelerating dark energy model, eventually everything falls apart and we have, once again, an infinite universe on into an indefinite, infinite future where nothing happens. Because the laws of physics are such that you won't have anything happening. You'll have the heat death of the universe, even though it's the heat death of an infinitely sized universe. Okay, that's possible. What Sam's talking about is something slightly different, where the universe has consistent density over time and just an infinite amount of matter. I've heard philosophers make this point before, and I've never found it quite convincing. They've got a particular view of infinity in their mind, where all possible things happen within this infinite universe. But you have to add assumptions about what the kind of infinity is there for that to work, so far as I know. Okay, we'll keep going. That's just a little aside.
But this is my point about fractals, actually. And, I'm speaking a little bit out of my depth here, but my understanding is that there's a problem with coastlines, which is that they get infinitely long the closer you measure. They approach infinity in length as you get better at measuring the nuances of a coastline.
Right.
That obviously doesn't make any sense. The coastline isn't getting bigger because you're measuring more finely.
Well,
right?
no, it makes sense. I mean, your ruler has to get infinitely thin and small. I mean, like you
right,
have
but
to.
The point is,
as you get down to the Planck scale, and
as you asymptote to infinity,
right,
you discover I screwed up somewhere, and it isn't my ruler. I screwed up
just
conceptually.
This sort of comes back to Zeno. Like this,
yes.
This is you've applied Zeno's paradox to measuring a coastline.
Bingo. But the point is, there is a way to do this, and it took somebody stepping back and saying, you know what, math is going to have to be. We're going to need a new toolkit, just the same way Newton and Leibniz discovered a toolkit for. People don't like it when I say it this way, but for calculating the incalculable, which is what calculus did, as I see it. But anyway, the point is, I think the many worlds interpretation is a best answer to a problem that is phrased so incorrectly that we can't, that just as if you ask the question about where these creatures came from 3,000 years ago, nobody had Darwinism to offer, so there wasn't even a way to begin to phrase the answer credibly. You could say, well, then that leaves you picking between deities who might have done it, and really what we're after is figuring out which one it was, when in fact it wasn't any of them. It was processes that were understandable, but we didn't yet have the mechanism to do so. So I think that's where we are in that case.
Okay, so and I think Brett's done this a couple of times now. He said he's not formally rejecting it, but he's saying it's stupid and insane. Then he's saying it's a best answer to a question that's poorly phrased, but then he said it's stupid and insane. So there's a little inconsistency here. If it's the best answer to the question, phrased poorly or not, then it can't be stupid and insane, can it? It is the best answer. It actually is the best answer. It's the best explanation of what the equations say. Could it be wrong? Absolutely it could be wrong. Absolutely it could be wrong. But, and this is why I say I don't believe in scientific theories. The word belief shouldn't have a place here. We shouldn't believe our scientific theories. But we should take them seriously. That's quite a different thing. That given our best answer, take our best answer seriously. And when we say take it seriously, take it seriously. So don't get all emotional about it. Use it in order to make progress. In particular, use it in order to make quantum computers. And yes, in order to understand the operation of a quantum computer, you have to assume that the computations are being done somewhere in reality. And it's clearly not in our physical universe, because there's not enough matter in our physical universe in order for the quantum computation to take place. So it's being done somewhere, and that somewhere is in these parallel universes, but we'll come to that at another point.
Yeah, it might be. I mean, it's hard to see what we're not seeing here, can't even dimly imagine, but it does seem like, I mean, it is a fairly straightforward claim that again, the infinite case is even simpler, because it's just, it doesn't require any notion of universes splitting, but it's hard to know where to bite the bullet. I think the thing to recognize with these counterintuitive consequences of infinity is just how counterintuitive infinity is. I mean, infinity is not just really, really big, right?
Right.
And our intuition that it's just really, really big. No, the rules change when you put that symbol of infinity on the paper,
right? But
rather than just a very big number.
If we can agree that in an infinitely large universe, somewhere at some point, in fact, an infinite number of places, an infinite number of times, a asteroid will have hit another asteroid, and aardvark will have been formed absent an atmosphere, immediately died, and disintegrated into a bizarrely large petunia of a unusual color, right? An infinite number of times. I'm telling you,
whatever is compatible with the laws of physics
will have happened an infinite number of times.
Yes.
I don't believe that has ever happened anywhere in the universe, and I believe that actually what we will ultimately come to understand is that the universe has to be limited in a way that actually won't have occurred ever.
Well, but one easy way to bound that is just to say that we don't live in an infinite universe. However big it is, it's not
very,
close
very
to being infinite.
Sam says here that anything physically possible that can happen will happen, and Brett objects on the idea that he's just thought of something preposterous. He just came up with a preposterous thing, a Harry Potter universe type scenario, as I explained in the last episode. This thing where two asteroids come together and an aardvark appears. Okay, well, yeah, it's hard to believe, and to say it's happened an infinite number of times is to misunderstand the point that David makes about measures of the universe. So it's an exceedingly small measure of universes where that happens. Infinite though it might be, infinite in terms of number. Okay, we don't count universes that way. We have a measure of universes, and it's an exceedingly slim measure of universes where that happens. So again, this is a misunderstanding of infinity, to say that just because it happens an infinite number of times and that it seems preposterous, that alone is a refutation. Seeming preposterous is not a refutation of a theory. You need to have something more than looking at a consequence of a theory, having an emotional reaction to it, and rejecting the entire theory on the basis of your objection to a particular consequence. It doesn't matter how preposterous it is. Again, the theory of evolution by natural selection on religious understandings has preposterous consequences. Like, an intelligent designer is not needed to guide the evolution of species. According to a religious person, that's preposterous. It's hard for them to understand. So Brett is in the position of being a kind of religious person here. He's religious about his own common sense, I suppose. That because this thing violates his own sense of common sense, he's rejecting it. But not on any scientific grounds, not on any rational, philosophical, epistemological grounds, but emotional grounds. It seems too preposterous. It's insane. It's stupid, and so on.
Yeah, so we need not worry about this particular...
Indefinitely large isn't infinite, and the difference is huge.
Yeah.
Yeah, well, I agree. So, all right, back to free will.
But I should just... I'll tell you, I think if you want to close the door to many worlds, or at least beat your intuitions into shape there, I think you should probably have either David Deutsch or Sean Carroll on your podcast, because they're both all in on that topic.
All in.
Yeah,
I love it when people... all I want to do is bet against it, because, I'm certain to be right, and it's easy money. So, okay, back to free will.
I couldn't agree more. Brett Weinstein, you should have a chat with David Deutsch. That would be great. And if you think you're certain to win your money, you could have I'll give you a $5 bet that you'll be convinced. So long as you remain open-minded about this. So I think that's where we'll end that part. Okay, we'll end the podcast there. I've been talking about it for a long time now, but I just thought this is emblematic of what you do here less frequently these days with respect to the many worlds interpretation. As Sam said there, it might be a majority opinion. I'm not sure about majority. The last survey I saw, and it was only a very small survey of physicists, was around the 30% mark, something like that. But whatever the case, this kind of criticism I did hear far more frequently, and you do hear it from lay people very frequently, that it's, that's ridiculous, that's insane, how could you believe anything like that, and so on. Well, I don't believe it, as I've said before. It simply is the only literal way to understand the equations of quantum theory. The other attempts, the other theories are hedges and additional assumptions and violations of Occam's razor and so on. We don't change the rules about the equations of general relativity. The equations of general relativity describe a curved space-time where space itself is literally curved. And this is why we get orbits having the shape that they do. This is why we can have GPS. But could you imagine an instrumentalist coming along and saying, those equations from general relativity, useful though they are, that's merely a fiction. They can be used to create a predictive model of where a planet will be around a star at any given point. They can be used for GPS. But as for this literally describing curved space-time and explaining gravity as it is, no, I reject all that. The equations don't actually do that. I haven't heard physicists really make this point. I think there are some. But even though I don't think that general relativity is the final word on the nature of gravity and space and time, it is the best approximation that we have so far. There is nothing to rival it. So too with the multiverse understanding of the equations of quantum theory, like the Schrödinger wave equation. It's just taking that literally. Now, do I assume that in the future we will utterly refute the curved space-time model? I think we're as likely to utterly overturn, in almost all respects, the theory of curved space-time as described by general relativity, Einstein, in the same way that we're likely to utterly overturn the multiverse interpretation. And that is about as likely to happen as the decoupling of DNA from genetics. For a biologist in the future to come along to find that DNA has absolutely nothing to do with genetics and evolution. That would be astonishing to me. Now, I do think that the current understanding of DNA and evolution and genetics will be overturned, but not in all respects, as I think the many worlds understanding of quantum theory will be overturned and general relativity will be overturned, but not in all respects. We will come to see these theories as approximations to some still deeper theory, as special cases of some deeper theory. If anything, maybe something like David Lewis's model will end up being more correct, in which case the many worlds interpretation from quantum theory is just a special case. But these other logically possible worlds might exist, or some portion of them might exist. Some universes with different laws of physics might exist. Okay, Max Tegmark's written these books about the many different versions of the many worlds. Okay, and I happen to enjoy David Lewis's book, The Plurality of Worlds, because it is the largest possible superset of all realities. Like all the logically possible things that could possibly happen. And the physically possible things are just a small part of that. So indeed, after all that, we've got Brett and Sam really balking at the idea of the many worlds interpretation, I think precisely because it violates their common sense. It violates almost everyone's common sense the first time we hear about it. But once you learn the details, then it comports with common sense. And other versions of trying to understand quantum theory are the things that are a violation of common sense. So let's go back to the beginning of infinity finally. I'm on page 279 for what that's worth, and I'll begin reading there. And David writes, "Here is another situation where, if we are not careful, common sense makes false assumptions about the physical world and can make descriptions of situations sound paradoxical, even though the situations themselves are quite straightforward. Dawkins gives an example in his book Unweaving the Rainbow, analysing the claim that a television psychic was making accurate predictions." And this is the quote from Unweaving the Rainbow. "There are about 100,000 5-minute periods in a year. The probability that any given watch, say mine, will stop in a designated 5-minute period is about 1 in 100,000. Low odds, but there are 10 million people watching the television psychic show. If only half of them are wearing watches, we could expect about 25 of those watches to stop in any given minute. If only a quarter of these ring into the studio, that is 6 calls. More than enough to dumbfound a naive audience. Especially when you add in the calls from people whose watches stopped the day before, people whose watches didn't stop but whose grandfather clocks did, people who died of heart attacks and their bereaved relatives phoned in to say that their ticker gave out, and so on." End quote from Unweaving the Rainbow. Continuing with Beginning of Infinity. "As this example shows, the fact that certain circumstances can explain other events without being in any way involved in causing them is very familiar despite being counterintuitive. The naive audience's mistake is a form of parochialism. They observe a phenomenon, people phoning in because of their watches having stopped, but they are failing to understand it as part of a wider phenomena, most of which they do not observe. Though the unobserved parts of that wider phenomenon have in no way affected what we, the viewers, observe, they are essential to its explanation. Similarly, common sense and classical physics contain the parochial error that only one history exists. This error, built into our language and conceptual framework, makes it sound odd to say that an event can be in one sense extremely unlikely and in another certain to happen. But there is nothing odd about it in reality." Just pause there, my reflection. So this is precisely the objection that Brett articulated in his podcast with Sam, where he was talking about the aardvark that apparently appears after an asteroid impact. The concern that however unlikely it's a possibility, is just an argument from incredulity. Some things are unlikely to happen. There is a very small measure of universes where this happens. And it's not a refutation of the entire theory to say that one struggles to accept that reality. Okay, I'm skipping a bit, and David's talking about the spaceship still. And on this spaceship, he talks about how there's a captain of the spaceship and there's a navigator of the spaceship. And if we could see from a God's eye view the entire multiverse, how the spaceship is represented in the multiverse, we would see a flurry of different instances of the captain and the navigator, but we would notice that only one instance of the captain ever interacts with an instance of one instance of the captain ever interacts with an instance of the navigator. So there must be information within the instances to tell the captain and the navigator which of them should interact with which. On that point, David says, The upshot is that our laws of quote, the upshot is that our laws of physics must also say that every object carries within it information about which instances of it could interact with which instances of other objects, except when the instances are fungible, when there is no such thing as which. Quantum theory describes such information. It is known as entanglement information. So far in the story, we have set up a vast, complex world which looks very unfamiliar in our mind's eye, but to the overwhelming majority of the inhabitants, looks almost exactly like the single universe of our everyday experience and of classical physics, plus some apparently random jiggling whenever the transporter operates. A tiny minority of the histories have been significantly affected by very unlikely events. But even in those, the information flow, what affects what, is still very tame and familiar. For instance, a version of the starship's log that contains records of bizarre coincidences will be perceptible to people who remember those coincidences, but not to other instances of those people. Thus, the information in the fictional multiverse flows along a branching tree whose branches, histories, have different thicknesses, measures, and never rejoin once they have separated. Each behaves exactly as if the others did not exist. If that were the whole story, that multiverse's imaginary laws of physics would still be fatally flawed as explanations in the same way that they have been all along. There would be no difference between their predictions and those of much more straightforward laws saying that there is only one universe, one history, in which the transporter randomly introduces a change in the objects that it teleports. Under those laws, instead of branching into two autonomous histories on such occasions, the single universe randomly does or does not undergo such a change. Thus, the entire stupendously complicated multiverse that we have imagined, with its multiplicity of entities including people walking through each other, and its bizarre occurrences, and its entanglement information, would collapse into nothing like the galaxy in Chapter 2 that became an emulsion flaw. The multiverse explanation of the same events would be a bad explanation, and so the world would be inexplicable to its inhabitants if it were true. Skipping a small part, and David writes, in quantum physics, information flow in the multiverse is not as tame as in that branching tree of histories I have described. This is because of one further quantum phenomena. Under certain circumstances, the laws of motion allow histories to rejoin, become fungible again. This is the time reverse of the splitting, differentiation of history into two or more histories, that I have already described. So a natural way to implement it in our fictional multiverse is for the transporter to be capable of undoing its own history splitting. Okay, so now I'm pausing the reading there, and I'm going to explain what David has written rather than just read it verbatim. So this is almost reading, but more of a summary of what's being said here. Okay, so here's a diagram that represents the splitting of the universe from one state that it's in, X, into two states, X and Y. And X represents the normal voltage, and Y is the anomalous one that the transporter causes. And this diagram represents what interference is. Again, we have the X and Y, the two different voltages. They can join together again, and this is what interference is. Interference phenomenon David defines there as where differentiated histories rejoin. Okay, now I'll read a little bit, and he writes, interference is the phenomenon that can provide the inhabitants of the multiverse with evidence of the existence of multiple histories in their world without allowing the histories to communicate. For example, suppose that they run the transporter twice in quick succession. I shall explain in a moment what quick means. And here we have a diagram showing X splitting into X and Y and then rejoining again into X. So we've got differentiation and then interference. If they did this repeatedly, with say different copies of the transporter on each occasion, they could soon infer that the intermediate result could not be just randomly X or Y, because if it were, then the final outcome would sometimes be Y, because X could split into X and Y, while in fact it is always X. Thus the inhabitants would no longer be able to explain away what they see by assuming that only one randomly chosen value of the voltage is real at the intermediate stage. Okay, and then David goes on to speak more about entanglement and the rejoining of histories. And I'm skipping a little bit there. And David writes, in our story, just as we did not allow splitting to happen in a way that would allow communication faster than light, so we must ensure the same for interference. The simplest way is to require that the rejoining take place only if no wave of differentiation has happened. That is to say, the transporter can undo the voltage surge only if this has not yet caused any differential effects on anything else. when a wave of differentiation, set off by two different values x and y of some variable, has left an object, the object is entangled with all the differentially affected objects. And here we have a lovely little diagram explaining what not entangled is about. When you've got two objects x and y, those are not entangled with the rest of the world if x and y, if the rest of the world is not differentially affected by x and y. On the other hand, entangled means that the rest of the world can be affected by x, while y will affect the rest of the world differently compared to x. And that's what entangled is about, entanglement is. And David writes beneath that diagram, so our rule in short is that interference can happen only in objects that are unentangled with the rest of the world. This is why, in the interference experiment, the two applications of the transporter have to be in quick succession. Although, alternatively, the object in question has to be sufficiently well isolated for its voltages not to affect its surroundings. So we can represent a generic interference experiment symbolically as shown. Okay, and here's the diagram of that. We've got x and the rest of the world, so x is in the world somewhere, but it splits then, it differentiates into x and y, but the rest of the world is not being affected by x and y, differentially affected as he says there. And interference is where x and y can merge together again to become fungible once more, and the rest of the world is still not differentially affected by x and y. I'll pause there, just my reflection. This is the difficult part for engineers trying to build quantum computers, because we need the objects to not be entangled with the rest of the world. This is the concept of decoherence, when the objects that are performing the computations within the quantum computer become entangled with the rest of the world, and therefore the information about the computation is lost. Now I might just go to the emergent multiverse on this for a moment. This is David Wallace's book. And Wallace in the book writes a bit about entanglement. But I just want to mention here what David said about a little bit earlier about how interference experiments provide would be evidence. And he's about to come to the fact, and he's going to say that interference experiments provide the main source of evidence for the many worlds interpretation, for the multiverse. Now, there is another kind of evidence as well. We don't fully have it yet, this evidence, but we will when quantum computers are built. And this is what David Wallace writes about David Deutsch, talking about the evidence that would come from quantum computation, which of course is a form of interference experiment. But anyway, and Wallace is just explaining about neutron interferometry, which is a form of interference experiment, but using neutrons. And David Wallace writes in his book, in a sense, of course, this discussion of quantum computation tells us nothing philosophical that we didn't already know from neutron interferometry. The really crucial step is from one layer of reality to no more than one, and the further considerations here are just quantitative changes. Nonetheless, there is something rather striking about the idea of empirical proof that such a huge number of different realities must exist. Deutsch puts it this way, quoting David Deutsch now. When Shor's algorithm has factorized a number, say 10 to the power of 500 or so, times the computational resources that can be seen to be present, where was the number factorized? There are only about 10 to the power of 80 atoms in the entire visible universe, an utterly minuscule number compared with 10 to the power of 500. So if the visible universe were the extent of physical reality would not even remotely contain the resources required to factorize such a large number. Who did factorize it then? How and where was the computation performed? Deutsch, 1997, page 217, so that is from The Fabric of Reality. I'm going to continue reading Wallace's reflection on what Deutsch has just said there. Wallace says, now if by this Deutsch means that the very fact of the calculation entails multiple universes, he has overstated the case. It is unproven that there are no classical algorithms for efficient factorization, and it is not logically impossible that the calculation just happens by magic, as it were, without any detailed account at all. There is no logical contradiction, although it goes against everything we have learned in science, in the supposition that the laws of physics must contain primitive factorization implementing processes. So, to pause there, my reflection on Wallace's reflection on Deutsch. Yeah, okay, magic is not logically impossible, but we don't live in a world of magic. So I think it's a fair criticism to say that although something might be logically possible, if it entails the supernatural or magic, that's something unexplained. Science consists of good explanations. So you can always put a god of the gaps in, and then magic happens, and then a wizard did it, as David likes to say. But this is not a good explanation. But Wallace comes back to rightly give Deutsch credit here, and Wallace writes, "But to object thus is to miss the point, which is not that there could be no other explanation for the factorization, but that we actually have a good, in principle, thoroughly testable explanation. Namely, it involves simple, well-understood algorithms operating in a massively parallel way within a single computer. It presumes that each computation happens independently. The empirical prediction is that everything will happen as if each computation is occurring independently, and there is no way of explaining the actual computational process taking place, which does not assume that the computations are happening independently. By Deutsch's criterion, then, there is no way of so explaining the algorithm which does not accept the reality of all the independent computations. At least within the quantum computer, there would be many worlds." End quote from Wallace there, and that's exactly right. It will be, and I think this is why physicists are coming around to the many worlds interpretation, because they can see all the progress and all of the energy being devoted to quantum computation, and they understand that argument. Putting aside other kinds of interference experiments, which should already be convincing, but if we are on the verge, I don't know how close we are, no one knows how close we are, to having fully functional quantum computers, then it will be very difficult to deny what Wallace has said there. And Deutsch has said, where are these computations taking place? If a quantum computer is computing things that would require more than all the matter in the visible universe, operating at switching speeds at the speed of light, and so on. If it can't physically be done in this universe, it's being done somewhere else. It's being done by harnessing the resources of quantum computers in other realities, in other physical realities. By the way, this book is absolutely brilliant. If you're really interested in this topic, then this is the book for you once you've read Fabric of Reality and the Beginning of Infinity. But it is highly technical. I might just mention as well, I've been what Wallace would regard as a wave function realist. But if you get into if you get down into the weeds about this, he says that we shouldn't be wave function realists. A wave function realist is just someone who says, well, take the wave function literally, okay? And the wave function, if you draw a graph of it, I won't bother to do that now, maybe next time. But let's say you're trying to describe the position of an electron around a nucleus. Then the wave function kind of looks like a Gaussian curve, the bell curve, normal distribution. Okay, it can look something like that. So it's highly probable to be in the center, wherever the center happens to represent, and less probable to be elsewhere. But the point is, with respect to the multiverse, that it isn't in one single place. The wave function maps all the different places that it could be. You square the wave function and you get the probability function. So you find out, and the amplitude tells you the probability, how high the bell curve happens to be at any particular point, tells you the probability of finding the electron at that place. We would say, however, it gives you the measure of universes, where that electron is going to be around the nucleus. Anyway, I digress a little bit. I just want to mention what Wallace says about that. And he writes, this is on page 316 of the Emergent Multiverse. If we take non-relativistic quantum particle mechanics as our paradigm, quantum theory, there is one fairly obvious possible way to make sense of the quantum state. It is typically represented as a wave function. on configuration space. So just take that literally. On this reading, which is called wave function realism, according to him, quantum mechanics is not a theory of events in 3 + 1 dimensional space-time at all. It is a theory of a complex field evolving in a very high-dimensional space. If we could treat the whole observable universe non-relativistically, for example, the space would have 10 to the power of 80 dimensions. Wave function realism was first explicitly proposed and discussed by Albert. It has been criticised on the grounds that it fails to provide the kind of ontology that can rewrite requisite facts about three-dimensional objects and their behaviour. From this book's point of view, though, such concerns miss the point. All that is needed is that we recover high-level ontology at a structural level. And I'm skipping a little bit, and he writes that the problems with wave function realism is, he says, wave function realism misrepresents the structure of quantum mechanics by singling out the position basis for a special treatment. Secondly, it is difficult at best to extend it to quantum field theory, where no single basis seems to have the preferred status which the position basis might arguably be said to have in non-relativistic quantum mechanics. And this position basis means we're privileging position rather than some other physical aspect of a given particle. And so Wallace goes on to say some more but he says, I see wave function realism as in general an unhelpful way to think about the ontology of quantum mechanics. That's just an end quote there. This is just an extremely technical point because I have heard people recently, as I have been as well, talking about taking the wave function purely literally, as I have indeed in this video especially. So it's a minor technical point, but this goes no way to denying the fact that, after all, this book is precisely about the multiverse, that these multiple histories, these multiple physical realities really do exist. Okay, so I'll continue reading. From the beginning of infinity, David writes, quote, once the object is entangled with the rest of the world, in regard to the values x and y, no operation on the object alone can create interference between those values. Instead, the histories are merely split further, in the usual way. And here's a diagram on page 284. Okay, so in this picture here, we have an object X, and the rest of the world is unaffected by the object. That object X is then split into two different copies. It differentiates into X and Y, and the rest of the world is not affected by either X or Y. Entanglement then means that object X has an effect on the rest of the world, while object Y has a different effect on the rest of the world. And then the splitting can continue. And as David writes in a blurb underneath that, in entangled objects, further splitting happens instead of interference. And he continues to write, when two or more values of a physical variable have differently affected something in the rest of the world, knock-on effects typically continue indefinitely, as I have described, with a wave of differentiation entangling more and more objects. If the differential effects can all be undone, then interference between those original values becomes possible again. But the laws of quantum mechanics dictate that undoing them requires fine control of all the affected objects, and that rapidly becomes infeasible. The process of it becoming infeasible is known as decoherence. In most situations, decoherence is very rapid, which is why splitting typically predominates over interference, and why interference, though ubiquitous on microscopic scales, is quite hard to demonstrate unambiguously in the laboratory. Nevertheless, it can be done, and quantum interference phenomena constitute our main evidence of the existence of the multiverse and of what its laws are. A real-life analogue of the above experiment is standard in quantum optics laboratories. Instead of experimenting on voltmeters, whose many interactions with their environment quickly cause decoherence, one uses individual photons. And the variable being acted upon is not voltage, but which of two possible paths the photon is on. Instead of the transporter, one uses a simple device called a semi-silvered mirror, represented by the grey sloping bars in the diagrams below. And there we have the beginnings of the Mach-Zehnder interferometer, which David Deutsch goes ahead and explains in the next few pages. So this is where I will end this particular episode, because we've explained that in a previous episode. You go back, I think, 2 episodes or so, and 3 episodes perhaps now. And another reason to read the book, if you're still struggling to understand any of this, that's the whole point of this series, is to help us all understand the book a little better. And I explain things slightly differently to the way David has explained things. but encountering the explanation in two different ways about the Mach-Zehnder interferometer is very important. And you can find, in fact, the author of this book, David Wallace, on YouTube explaining the Mach-Zehnder interferometer experiment as well. So this idea of entanglement, where we have these particles unentangled with the rest of the world, this is what goes on inside a quantum computer. So we have these particles interacting inside of the quantum computer, not entangled with the rest of the world. If they get entangled with the rest of the world, then it's like the information is kind of, I don't know if David would like it to be put this way, but the information kind of leaks out into the rest of the world. It becomes entangled with the rest of the world, and then you lose the quantum computation. And at the moment, the engineering seems to be concentrating on how to ensure that the particles remain coherent together. They don't decohere. And the common way of attempting to do this appears to be keeping the particles at low temperature. I happen to be wearing a shirt that I've been wearing for this episode. Not sure if you can see that. That's from the University of New South Wales here in Australia, and they have a centre for quantum computation. And I visited there a few times, and they have this remarkable way of trying to do quantum computation. Suffice it to say, the temperatures need to be exceedingly low, because as soon as the temperatures get high, the particles start to vibrate too much, and the information that then the particles then become entangled with the rest of reality. Now, to get the temperature down really low, they use liquid helium, as one would expect. But an interesting part about this story is that liquid helium itself isn't cold enough for what they need to do. And so they need a special isotope. So the first stage of cooling is to use normal liquid helium, which is expensive enough. But for the second stage of cooling, they use an isotope, helium-3, I believe. And the helium-3 isotope then boils away from the rest of the helium that they have, and that lowers the temperature even further. It's like a refrigeration effect, an evaporative cooling effect, using liquid helium, where an isotope of liquid helium boils away, taking additional heat with it. Now, where do they get the helium-3 from? Well, one of the sponsors of the University of New South Wales Quantum Computation Project, so they told me, was the American Army. And the American Army not only invested in their project, military likes to invest in computational projects, but they also supply them with helium-3. Where would they get helium-3 from? Apparently, decommissioned nuclear bombs, nuclear weapons, give off this isotope of helium-3, and so they collect it. And again, if I remember correctly, and I'm sure someone will let me know if I get this wrong, they said that a balloon full of the gas, not full of the liquid, but a balloon full of the gas is something like $10,000 worth. That's how much it costs for this isotope of helium-3. That's how rare it is. And so they use this out at the University of New South Wales in order to do quantum computation, because they need to keep things cool so that they don't decohere. Okay, that's where we'll end it today. We'll have one more episode on the multiverse, and then we'll be moving on to the next chapter. So again, hope you're enjoying this. If you do feel the urge to contribute to my Patreon account, you can find me on Patreon or PayPal as well, and I have a donate button on my website. Thank you very much for any and all support, and thank you for your comments on YouTube. Thank you for your feedback on Twitter. It's all very valuable. See you next time. Bye.